60 seconds. Lights on. Down 2.5.
Project Apollo remains one of the most important space programs in U.S. history. Between 1968 and 1972, 32 successful missions were carried out, with the help of a trailblazing computer, the Apollo Guidance Computer, or AGC for short. The AGC ushered in a new era of computing with its forward-thinking architecture. The display and keyboard interface, or DISCI, allowed the Apollo astronauts to interact with the computer by issuing and receiving commands in a unique verb-noun format. Our design brings the AGC into the modern era as an interactive exhibition piece. Here you can see a block diagram of our system. It shows the FPGA connected to our custom DISCI and simulation demo monitor. Let us start with the FPGA and with our processor's memory map.
The AGC memory map is 12 bits and split between RAM and ROM. The register file is mapped to the lowest segment of RAM. The A register is used as the primary general-purpose register. The L register may be used in conjunction with the A register as the lower half of a double word when necessary. The Q register is used for linking during function calls and returns. The EB and FB are the bank selection registers for RAM and ROM respectively. The software address space is 12 bits. But the hardware address space is 15 bits. In order to use all 15 bits of memory, in both RAM and ROM, there exists a segment of software addresses that may point to any one of the bank's memory segments. To change banks, the programmer writes to EB for RAM and FB for ROM. The AGC's instruction set was constructed specifically to meet the demands of space travel. The architecture used 15-bit words and 1's complement arithmetic. Our architecture includes 34 instructions. 16 of these are arithmetic instructions such as add, which adds the A register to the value stored at the address K in memory and stores the result in the A register. 6 are data movement instructions such as transfer to storage. 6 are control flow instructions, 6 are I/O instructions, and 3 are miscellaneous instructions. We implemented a 4-stage pipeline to process our instructions. In the fetch stage, the program counter is processed by the address translator before being presented to ROM. At the next stage, the selected instruction word is decoded into control signals that are used to access the registers, RAM, ROM, or I/O. In the execute stage, operands are selected and fed into the ALU, where a specific operation is selected by the control signals. For branching instructions, the branch condition is evaluated, and if taken, the PC is updated for the branching address. In the write-back stage, we update the program state based on our results from the previous stages. The pipeline CPU and I/O were implemented by us in System Verilog, whereas the RAM and ROM are Altera IP megafunctions. Our customized assembler reads in the AGC assembly file and generates a MIF file that is stored in ROM. We use the custom AGC assembly test suite and VCS for microarchitectural verification in simulation. Once verified, we use Quartus to instantiate it on the Cyclone 5 FPGA and on the DE10 SoC.
We now transition to the DISCI unit and the orbital simulator. Our AGC on the FPGA will communicate with the DISCI through a UART interface. The DISCI will scan the keypad matrix and send user input through UART, and in turn the AGC will reply with the requested results. The DISCI also handles driving the LED displays and lamps through I2C LED drivers. Finally, the DISCI will communicate with an orbital mechanics simulator through Bluetooth telemetry and relay mission data. In the end, the results are lunar injections and orbital transfers in our physics simulation, as per calculated by our AGC. Here are the implementation details and the bring-up of our DISCI unit. The DISCI consists of a custom designed and built PCB with an acrylic front panel. Here is how the unit was implemented. First, after the part selection, the schematics were captured using Altium Designer CAD software. The PCB was then routed and sent out to be fabricated. After the PCB and the components orders were received, the board was manufactured in-house. First, the solder paste was applied using a stencil. The components were then placed carefully by hand on the board. and finally all soldered by baking the parts in a reflow oven, with the rest of the parts being hand soldered. The finished unit was functionally inspected and thermally profiled, all meeting the specifications, both for UART and I2C protocols and the temperature, with the maximum temperature being around 40 degrees Celsius. Using the implemented AGC ISA, a custom AGC demonstration assembly code was written to showcase basic orbital mechanics. Here we see a subroutine for calculating burns for changing orbits, known as the Hohmann transfer. The majority of the demo code was written by us, with some sections being borrowed from real Apollo missions. As stated earlier, the Apollo astronauts historically used verb and noun pairs to operate the AGC. The verb signifies the action required to be taken for the computer, and the noun signifies the required parameter or value. Certain actions, such as testing the displays, do not require a parameter, since it is a verb-only command. However, for running programs, we specify the run program action, which is verb 39, with the noun parameter being which program to run. For example, to run the Hohmann orbital transfer program, we run program by inputting verb 39 for program number 01, or noun 01, which is the Hohmann transfer program. In order to showcase the capabilities of the AGC, we use our computer to calculate orbital trajectories in a Newtonian physics simulation. We solve the classic three-body problem, involving the gravitational forces between the Earth, the Moon, and the spacecraft, using a fourth-order Runge-Kutta ODE solver. Here, the orange body is a spacecraft, the blue is the Earth, and the gray is the Moon. The simulation produces mission data consisting of velocities and positions of all the orbiting bodies, and the AGC in turn returns the required burns to conduct the specified mission program. Furthermore, the users can modify various orbital radii and distances to further help develop better understanding of orbital mechanics. We will now showcase 3 programs for our demonstration. The first will test the displays, the second will conduct an orbital transfer, the Hohmann transfer, then a translunar injection. We start at verb 07, which indicates that the displays has been cleared. We now type in verb 06, noun 00, and hit enter. We will now conduct an orbital transfer to a higher orbit using the Hohmann transfer. We run the Hohmann transfer program. We will specify our final target orbit in the simulator, then upload the mission data through telemetry. We have began the initial burn, indicated by the change of spacecraft color from orange to red, and after the final burn, now we are in our higher target orbit. We can now go straight to the moon from here. Going to the moon is a 3-step process. First, we calculate the initial burn to get to the moon, or program 02. Then, we upload the mission data. Then, we execute program 03, which calculates the final burn to be captured by the moon. Finally, the last program, 04, calculates the time or the alignment for when to conduct the initial burn. The spacecraft will wait until the alignment has been achieved between the moon and the spacecraft. The spacecraft must lead the moon to make the rendezvous and commence the burn. We have now successfully arrived at our destination, the moon.